Hello, this video is for Module 1 Part 4 and includes a discussion of terms in a multiple linear regression model. Okay, let's go ahead and get started then. So a multiple linear regression model requires a set of predictors in order to make predictions for the response variable. Now there are a variety of ways in which the predictor variables can be used in that multiple linear regression model. In Module 1 Part 4, we are going to discuss those various ways. So a definition here, a model term is the form that a predictor variable takes on when being included in a predictive model. So we'll show you some examples here of the difference between model terms and predictor variables. The data that we're going to use here is centered around out-of-pocket costs for about 3,300 patients from a collection of clinics. The files folder is here and includes the Colab document and then also the out-of-pocket cost data. Let's take a look at the fields that are included in this data set. The first being just the patient ID. And this particular variable is not going to be included in the model, but the rest will here. The main outcome that I care about in this model is the cost. So that's going to be my response variable. And then I have 5 different predictor variables. 2 of those predictor variables are numerical, and that is age of the patient and then the BMI number for that patient. The other 3 predictor variables are actually categorical in nature, and those are the identified sex of the patient, so male or female, whether or not the patient is a smoker, so a no or yes, and then we have information from the region in which the patient resides, and I believe there's 4 regions in this data set. The goal here is just to obtain the best possible predictions for the out-of-pocket cost here. So this column clear on the right is my response, and I want to obtain the best possible predictions for that particular variable. Let's talk a little bit about the structure of the model. So there are, as I said, 2 numerical predictor variables, and those we can just put into the model in our software just as they are. Recall that a prediction equation needs to have numerical values in order to make a prediction. So on some of these other variables, for example, sex, smoker, and region, those are categorical in nature. And we're going to have to change how those predictor variables get used in that prediction equation. That's what we mean by a term. So for example, one possible term is called a dummy term or a dummy variable. And this is just used to identify if a particular characteristic or condition is present or not. So for example, when we use the smoking status in our model, what the computing technologies are going to do is convert the smoking status, which is either a yes-no type variable. So if we go back up here and look at that, right? It's going to convert that to what we call a dummy variable or dummy term. And how is that done? Well, that dummy term is going to get a value of 1 if the individual is a smoker. So if that condition is present, and it's going to get a 0 if not. So that's how the smoking status actually gets used or put into the model. Same thing or something similar for sex. So for sex, it's going to be either male or female. So the software computing technology is going to identify one of those as the 1. So maybe the males will be identified as the 1s. And then the other, so females, would be identified as 0 in the model. It's important to understand how the dummy variables are being used, because when we're trying to make predictions, we're going to have to understand that structure. Luckily, for the most part, the definition of a dummy variable is similar across different software packages or computing technologies. But again, attention does need to be paid to how those dummy variables are created. Okay, so let's look at the relationship between the numerical variables, which are age and BMI, and my response variable, which is cost. When I want to understand the effect of the categorical variables, one way to do that is to just color code those points by sex, for example, or by smoking status. So here I have done that. This is by sex here, so females are the more Salem colored dots here, and males are the more bluish green colored dots here. Or if I look at the connection or these plots across smoking status, yes, okay, would be the bluish green again, and the Salem color would be no. And then here I have the plots color coded by the different regions. Now, one thing that certainly stands out, and you can see this even without the color coding, is that I have these three distinct groupings of points in this age versus cost scatter plot. There appears to be some grouping of the points as well when I'm looking at BMI versus cost, but they're not as distinct. The goal is to identify why this is happening, and we can do that partially here with this example. More on that in a little bit. So for example, one thing that's driving these three distinct groupings of points is the smoking status. So this is the cost here. It's on the y-axis. So you can see that the non-smokers tend to be reduced in cost compared to the smokers. This middle band kind of has a mix of the smokers and non-smokers. If I look at that same plot across the different regions, for example, you can see that the colors are all kind of intermixed in each of these groupings. So what that tells me is that the region is not the reason or cause for these groupings. It has more to do with smoking status. Certainly you can see a distinction between the non-smokers and smokers, and I have this middle region that is kind of intermixed. Again, if we're looking at the sex here, the points tend to be intermixed regarding those three distinct groups. So I would say that the sex is not a cause as to why these points are grouped in the way they are. So when we're trying to understand how these different variables influence my predictions, I'm going to need to be concerned with trying to identify why these groupings are happening in the way that they are. Okay, let's make sure I hit all the observations that I wanted from those plots. Age does have a stronger relationship with cost than BMI does. These points are, again, have those three distinct patterns, and they're pretty, maybe a little bit of curvature there, but the BMI dots are certainly kind of more dispersed here. So we would say that age has a stronger relationship with cost than BMI does with cost. We talked about the three distinctive groups. Smoking status appears to be the most useful predictor in defining those three distinct groups. Okay, I'm going to fit actually 4 different linear regression models. I'll provide rationale for each. We are going to spend most of the time just talking about model number 4 because that's the model that performed the best. So as a practicing data scientist, here's how I would think about building up these multiple linear regression models. I'm first going to start with something quite simple. I'm going to try to understand cost using just the 2 numerical predictor variables, which are going to be age and BMI. This model has 2 predictor variables, and it also has two terms, one term for age and one term for BMI. So that's going to be model number 1. Let's consider model number 2. This has a structural form of age plus age squared plus BMI. Now, if we go back up and look at the plot with age, there might be a little bit of curvature in some of these groups here. So that is why I would like to take age and maybe include a second term to allow for curvature with respect to the age direction. So in this model, model number 2, I actually have two predictor variables, age and BMI. However, this model has 3 terms. One for age squared, which again is going to allow for a little curvature, and then another one for BMI. So here's a clear distinction between what we indicate predictor variables to be and what we indicate model terms to be. I have 2 predictor variables, but this model has 3 terms. Model number 3 is the first model where I'm going to include the categorical predictor variables. So sex here, smoker, and region. Again, dummy variables are going to be created for each of these. Okay, so I'm going to end up with a dummy variable for sex, which is that 0-1 coding that gets used. I'm going to have a dummy variable for smoker. And then I'm going to have, for region, there's actually 4 regions. So a collection of 3 dummy variables are created there. I'm not going to go into details on how that's done, but I will help explain how I can get my prediction equation in that situation. And then the other 2 numerical variables are just age and BMI. Okay, now let's talk about model number 4. Model number 4 is going to have the situation where I include what we call interaction terms. So here we have sex star age, and I have sex star BMI. So what is going on with the interaction terms? Why do we have those? So a sex by age interaction term is going to allow the model to have the effect of age vary across the sex. So maybe when we're thinking about insurance costs, out-of-pocket insurance costs, maybe the older a male gets, the cost goes up much more than it does for females. If that's the case, you are going to need or want a sex by age interaction term in the model, because we want the effect of age to be different between the males and females. So an interaction term is a very practical thing. We want to make sure and allow that model to be able to adjust for the effect of age depending on sex. If in that situation, you're going to need a sex by age interaction term in the model. Likewise, if we want the effect of BMI to vary across the 2 sexes, then we're going to want a sex by BMI interaction term in the model. Likewise, if I want the effect of age to be different between my smokers and non-smokers, which that one might actually be more important to cost than sex by age. So if I have a very old smoker, then my insurance costs are probably going to go up much more than if I have an older non-smoker, just because of the ill effects of smoking. And then this last term is going to allow for the effect of BMI to vary between smokers and non-smokers. Now, this particular model is the most complex of the ones that I have listed here. It has, what, 1, 2, 3, 4, 5 predictor variables in it, but it has many more than that in terms of, when regarding the model terms, it has 1, 2, 3, 4, 5, 6, 7 in it. So as you can see, we can increase the model complexity by specifying more model terms without necessarily increasing the number of predictors. Okay, so let's look at the multiple linear regression output for each of these models. So the model 1 was the simplest one, where I just put age and BMI. And you can see that my R-squared here is at 14%. Not very good. Remember, the R-squared goes from 0 up to 100%. So an R-squared there of 14% is pretty low. Model number 2 is where I put the squared term for age in the model. And I do that with what's called a polynomial term inside of R. Here are the 4 estimates. So I'm going to have the intercept. I have a coefficient for, or estimate for age. I have an estimate for the age squared, which is 4.32 here. And then I have an estimate or coefficient for BMI, which is 322. Here's model number 3, where I have the categorical variables present and the 2 numerical variables. I alluded to the fact that you need to understand how the indicator terms or dummy terms are put together. So here in this model, notice that I do not have a sex female anywhere listed under my estimates. What that means is that sex female was the 0 setting for my dummy term. The sex male was my 1 term. Okay, that is being expressed as a 1 in my dummy term. So anytime that I am going to make a prediction for a male, I need to add this part or this estimate into my equation. How about the dummy variable for smoking? Notice that smoking no is not present anywhere in this list of estimates. What that means is smoking no was set at the 0 setting. Smoking yes was set at the 1 setting. So if I want to make a prediction for a smoker, I need to include this value here, 23,161, into my prediction equation. Just for completeness, notice that I don't have any region 1 listed here. So again, region 1 was set at the 0 setting for my dummy variable. If I want to make a prediction for region 3, then I'm going to need to subtract the 521.36 here in my regression or prediction equation. That number or amount that I'm going to subtract is going to be different across the different regions. So if I was making a prediction using region 4 for a person that lived in region 4, I would want to subtract 733 here. One thing that I noticed with the inclusion of these categorical predictors is my R-squared went way up. I was at about 14% before, and now it jumps up to 79% here. So these other predictor variables are very important in understanding what's going on with cost, which makes sense, smoking especially. Now, model number 4 is an extension of model number 3, where I just include these interaction terms again. The interaction terms, okay, so these first set are going to be just like model number 3. Let's look at the effect of males when I'm talking about age. So the coefficient for age, so when I'm trying to make a prediction, and I need to take a patient's age and multiply it by the coefficient, okay, if I have a female, which if female is not listed here anywhere, then this is going to be the coefficient on age, the 265. If I want to make a prediction for a male, I'm going to, like I said before, I'm going to have to subtract off 754. But also when I'm looking at the effect of age, I'm going to have to subtract off another 24 from the age coefficient. So let me show you that down below. So here I'm talking about model number 4. If I have a female non-smoker from region 1, what terms am I going to pull off here from this model? So I have a female non-smoker region 1. This is for a male. I don't need this term. This is for a smoker. I don't need this term. This is for region 2. I don't need this term. Region 3, do not need this term. Region 4, do not need this term. So all of those I can exclude when I'm talking about a female non-smoker from region 1. I'm just going to have the 323. I'm going to have an effect for age, which is the 265, and I'm going to have an effect for BMI, which is negative 21. This coefficient here is for males. These coefficients down here are for smokers, so I don't need any of these. So out of all of these, when I'm talking about a female non-smoker from region 1, I just need those 3 terms. Now, what adjustments need to be made when I'm looking at my prediction equation when I go from a female to a male? So this second bullet here is for a male non-smoker region 1. Okay, so let's go look at our list of coefficients. I'm talking about a male, so I'm going to need this 754. So I'm going to take the 323, which I start with, and then I subtract off another 754. So that's what we're doing right here. I'm talking about a non-smoker here, so I don't have to worry about the smoker yes term. This individual is from region 1, so I don't need any of the region variables. When I get down to the age, I'm going to need the 265, but I'm talking about a male here, so I need to take the 265 and I need to subtract 24 from that. That's what I'm doing here with the second term. That's going to be the effect for age. I'm talking about the effect for BMI. I'm going to start with that negative 2162. That's what I had for females. But then I'm going to add, it looks like about 70 to that. Where am I getting that from? Sex male BMI. So I need to add 70 to the BMI coefficient when I'm talking about a male. Likewise on some of these others. So I kind of built up each of these models from the one previous. Now I actually did this for all the models. I wrote out the prediction equations for each, included the model R-squared and also the root mean square error. Those first 2 models did real poorly, only 14%. My root mean square error is about 9,500, 9,600. Model number 2 had that effect for the curvature, but it really didn't improve my ability to make accurate predictions. I only went from a 14.01 up to about 14.4% in my R-squared. My root mean square error didn't drop very much. So including that squared term really didn't do much for me. However, when I went to including the categorical predictors, the sex, smoking, and region, I went from about 14% on my R-squared up to about 79%. My root mean square error dropped a lot as well, went from about 95, 9,600 down to 4,700. There's also some gain in looking at those additional interaction terms. Now, those interaction terms certainly make my model more complex, but I'm getting a gain from that in terms of my ability to make accurate predictions. My R-squared from Model 3 was at 79%. It went up to about 88%, or 87.5% or so when I looked at Model 4. My root mean square error went from 4,700 down to 3,650 or so. So there's certainly this model number 4 is certainly more complex, but again, I'm getting some gains in terms of my ability to make accurate predictions. If we look at the variable importance plot, I'm just going to do that on model number 4. Okay, one thing that we do not want to do, certainly, is just look at these estimates to determine how important the parameters are, or the predictor variables are. The variable importance is determined using these t values. The larger the t value in absolute value, the more important the predictor is. And considering the list that we have here, you can see that this smoker BMI interaction term is actually the most important term here. It has a t value of about 50, which is pretty big. So the smoker cross BMI, which is that interaction term, is the most important predictor in this model. Certainly age is important. That's next here. Smoking status comes into play, and then it moves down from there. Many of these variables, even though this model is pretty complex, many of these variables are bigger than that red line, or taller than that red line. That red line, again, has that 2. You can also maybe adjust that down to 1.5 as well, as some people, as I've said before. Let's look at the quality of predictions. Again, my R-squared is about 87% or so. We'll talk more about this in a little bit, but there are some distinct patterns that are appearing in this actual versus predicted cost plot. And we're going to want to try to figure out why those patterns exist. Also, the accuracy of my predictions seems to vary across these different groupings of points. Down here, you can see that this glob of points right here follow that y equal x line pretty closely. But up here in this group, it's definitely a distinct group, my predictions are not as accurate. Talk a little bit about the prediction errors and how large they are. My root mean square error for the model number 4 is about 3,600. My mean absolute prediction is down around 2,200. And again, if you're looking at how big these values are, they are going from about 3,000 up to 60,000. To do that within $2,000 is a pretty accurate model. What we've done here is calculated the MAPE across the sex variable here, the smoking status, and also the different regions. Just trying to figure out whether or not some of these situations I'm able to make more accurate predictions than other situations. So for example, for my non-smokers, my MAPE is just short of 2,000, but it's more than double that for my smokers. So what that means is I'm able to make more accurate predictions about out-of-pocket costs for my non-smokers than I am my smokers. Over here, region 2, 3, and 4 have a MAPE value of around 1,500 to about 2,000, but for some region 1 has a much larger MAPE value of $3,800. So again, my predictions for region 1 are not as accurate as these other regions. Here I'm looking at the prediction error versus predicted cost. Okay, so on the y-axis here are my errors, and they range from about negative 20,000 up to 20,000. So in some situations, I'm not able to make very accurate predictions. I'm $20,000 off of their out-of-pocket costs. I'm going to do that color coding again to try to figure out what's going on with these distinctive groups of points here. So here I have the color coding by sex. Again, the points are pretty intermixed, so sex doesn't appear to be a reason the points are grouped the way they are. In my regions, they tend to be intermixed again, so again, the region isn't really indicative of why the points are grouped the way they are. On my smoking, though, I do have some distinct observations here, and that is that for the most part, so this greenish blue is for my smokers, they tend to have higher predicted costs than my non-smokers. So there's a pretty clear distinction here of about, what is that, $15,000 or so, that if you're a non-smoker, I can expect the out-of-pocket costs to be typically not more than $15,000. Whereas for the smokers, it's likely to be more than that $15,000. This does not indicate why I have this grouping versus this grouping here, though. Or likewise on my non-smokers, why I'm getting those two distinct groupings. So at this point, an investigation is warranted into why these distinct groups are appearing in these plots. When additional investigations of the data or process that we're using or the models is needed, we have the idea of a data science life cycle. So what we mean by the data science life cycle is that the next step is to try to figure out why these patterns are appearing in these plots. So I need to investigate why these groupings exist. Once I have identified the cause of those groupings, then I want to incorporate that information into my predictive model. Now, this is not usually done necessarily. Step one is not usually done by a data scientist. A data scientist has to work in a team with others to try to figure out why this is happening. The step about incorporating that information into your predictive model, that now becomes the responsibility of a data scientist. But if I can identify the root cause as to why I have these 4 distinct patterns, I'm going to be able to make better predictions. My prediction accuracy is definitely going to go up. So that idea is called the data science life cycle. And here's just an image that I grabbed off the internet regarding the data science life cycle. There's usually a get started phase, like I'm trying to answer some questions or understand some relationships, or here trying to make accurate predictions for out-of-pocket costs. I need to prepare the data. Model planning is just deciding what predictors you want to use and what predictor terms you might include. Actually building the model, this is going to be in our software. Communication of results is just understanding what's happening with the predictions, doing your investigations about the quality of the predictions, things like that. And then that, again, feeds back into asking more questions about the data. As we learned up above, the smoking status is partially responsible for these groupings. So when I did this plot, again, with smoking status, I have those 2 distinct, less than 15,000, more than 15,000. Another thing here is that the striations that I'm seeing here, so kind of these groups that go from the upper left down to the lower right, that's a classic indication that you are missing a predictor variable. So there's something else, as we would want to try to figure out from our investigation. We are missing some other variable that is important to cost here. And that's going to help us differentiate these 2 striations that I see here. I don't know what that variable is. It's not available in this particular data set. Okay, but in a practical sense, I'm going to need to go back to my data team or go back to my team here and try to figure out why those striations are occurring in this particular model. Okay, the task here then for this module is just to make some predictions for this first person here in this list. The answer is provided here, the 5240. Okay, but it's just how would I go about getting those predictions. So this first one is just showing me how the 5240 was calculated. And then I just start switching things up on you. Suppose this person was a female instead of a male. How is that going to affect my prediction? Suppose this person was 22 instead of 21 years old. How is that going to affect my prediction? So just kind of moving some of these numbers around and understanding how that influences my prediction equation. Number 3 is just to do a variable importance idea with model number 3. So I showed you model number 4, but just do that for model number 3. 6 is a little question about that data science life cycle and what the appropriate steps would be between the communicate results and discovery. Okay, that does it then for this set of notes. Thank you very, very much for listening, and I hope you have a good night.